Assalamualaikum and hi everyone. Today we want to present about material selection and tensile performance evaluation for engineering prototype application. Our team member consists of 3 members. First, Nur Izani binti Zulkifli, RP24105, and me, Putri Fitria Anggraini, RP24032, and lastly, Wan Sofia Ahmani binti Wan Khairul Hisham, RP24021.
Me, Nur Izahani binti Zulkifli, RP24105, would like to talk about the project introduction. So, tensile testing serves as a critical destructive evaluation method to characterize the mechanical behavior of material subjected to uniaxial tensile loading until the point of failure. These studies aim to conduct a comparative analysis of the tensile performance, specifically focusing on parameters such as Young modulus, yield strength, and ultimate tensile strength of 3 distinct thermoplastic polymers, which is polypropylene (PP), polyethylene terephthalate glycol (PETG), and polylactic acid (PLA). By evaluating the distinct stress-strain profile of this material, this project established a quantitative basis for material selection. The finding will provide essential data to determine the suitability of each polymer for integration into a heavy-duty structural prototype, ensuring that the selected material meets the necessary mechanical requirement for its intended operational environment. Now I would like to talk about project objective. The first one is to prepare standardized tensile test specimen from the thermoplastic polymer, which is PP, PETG, and PLA. The second one is to conduct tensile testing machine using a universal testing machine UTM to obtain key mechanical properties including yield strength, ultimate tensile strength, modulus of elasticity, which is Young modulus, and percentage elongation at break. And the third objective is to evaluate the mechanical performance of this polymer considering factors such as ductility, brittleness, and elasticity to justify the most suitable material for specific structural prototype application. Now let's move to the third slide, which is specimen preparation. The material were prepared using 2 distinct manufacturing methods, which is injection molding for the polypropylene and 3D printing for the PLA and PETG. The injection molding process provides the PP specimen with a superior isotropic structure density, free from the layer-based void, and weak interface inherent in 3D printing. This manufacturing advantage directly contributes to the higher ductility and superior energy absorption observed in the tensile testing of the PP, confirming its suitability for a reliable heavy-duty structure prototype. So now let's move to the tensile testing process. So the tensile testing process begins with the precise measurement of the initial gauge length, width, and thickness of each dopant specimen to ensure accurate cross-sectional area calculation. Each specimen was then circularly and vertically clamped into the grip of the universal testing machine, ensuring perfect alignment to prevent any unwanted bending or torsional force. During the test, the UTM applied a constant axial crosshead speed, gradually increasing the tensile load, while the machine software the force and the resulting elongation of the material. This continuous data collection allowed for the generation of the stress-strain curve, which mapped the mechanical response from the initial elastic region through the yield point and ultimate fracture. Once a specimen reached its failure point, the test was concluded and the fracture surface was examined to observe the specific failure mode, whether ductile, as seen in the necking behavior of or more brittle as observed in the layer-by-layer failure of the 3D printed PETEG and PLA.
Next, experimental result. The data presented provides clear quantitative evidence for selecting polypropylene as the optimal material for your phone holder prototype. The PP specimens consistently outperformed both PETG and PLA in load bearing capacity, reaching maximum force between 1138.27 Newton and 1153.54 Newton, while PETG hovered around 829 Newton and PLA lagged significantly at 552.96 Newton. Furthermore, PP demonstrates superior ductility with a tensile strength at maximum force ranging from 7.16% to 7.69%, which is more than double the strain capacity of PETG and PLA. This combination of higher load-bearing capability and enhanced flexibility indicates that the PP prototype will be more durable and better equipped to handle the mechanical stress and potential impact of daily use without suffering from the brittle failure modes observed in the other tested materials. Next, stress-strain behavior. While other materials show higher initial stiffness, the test data demonstrate that PP possesses the highest percentage elongation at break, as seen in the furthest strain reaching 0.20 mm per mm on the graph. The superior ductility combined with its high energy absorption capacity ensure that our phone holder is durable, impact resistant, and capable of withstanding repetitive mechanical stress without catastrophic brittle failure, making it the most reliable choice for functional structural prototype.
I am Monsufa Amani binti Wan Kharisham, RP24021, and today I'll be presenting the material selection for prototype. While PLA offers high tensile strength, its brittle nature poses a risk of sudden failure. PETG offers a balance, but polypropylene (PP) was selected for this prototype due to its superior fatigue resistance, high ductility, and chemical stability. These properties ensure that the prototype can withstand repetitive operational stresses and environmental exposure without catastrophic brittle failure, making it the most reliable choices for our specific application, which is a phone holder. Prototype preparation. The prototype was assembled by arranging these individual PP components to form a stable support structure. The design utilized the inherent flexibility of the PP material to allow the components to be joined or angled to create the necessary cradle for a phone. By interlocking or fastening a dog bone specimen, we created a functional phone stand where the tensile tested geometry provides the required support angle and structural rigidity. The white semi-opaque finish of the PP components highlight the clean, functional nature of the fabricated prototype. Lastly, prototype demonstration. The demonstration served to prove that despite being composed of individual components, the assembled phone holder maintains sufficient structural integrity to support the phone without yielding or fracturing under static load. By placing a phone on the cradle, we demonstrate the real-world application of our material selection. The demonstration confirms that the flexibility of the polypropylene allows the holder to absorb minor stresses while remaining rigid enough to hold the device at the desired angle. That's all from us. Thank you.